In this video, we will continue looking at example 3 from the packet that we started today in class. To quickly recap, in this particular study, we wanted to determine if there was a difference in the biomass of the plants that grew in 3 different plots. So kind of the idea here was in plot 1, we were going to add 20% additional rainfall, water based on rainfall during the winter months. In the second plot, we were going to add additional water to the plot in the spring months. And then in the third plot, it's going to act as a control group, just going to give them the normal rainfall and see what happens with the plant biomass. And so we took the data from 6 samples in each group, and here we have the mean, the results. And then the question that we were going to work towards is there a difference in the biomass based on each particular region? So remember that when we're doing Anova, the null hypothesis is always that we're going to assume that all the means of the 3 populations are the same. So here we'd assume that regardless of how much water you add, whether it's in winter, spring, or not at all, it will remain the same. And again, we don't really expect that to be true, but that's what we want to test. And our alternative hypothesis is that there is some form of a difference between them. Now remember, we're not conclusively looking at differences between all of them or between specific pairs, but just that there will be some difference at the end of the day. Some of the details that we did not have time to get into are the degree of freedom of each of the what we call the numerator and the denominator, as well as the population size and the total sample size. So it outlines all of this in the packet. But basically, we're always going to be dealing with I. I stands for the number of populations at hand. So basically, it's kind of like how many different groups are we analyzing beyond 2. In this case, we have 3 different groups, so that's just always what I will be. In any case, we have 3 populations, and n is going to be the total sample size. So like little n, or n1, n2, and little n3 would represent the sample size from each group. Basically, if we add them all up, each one had 6 sample size of 6. So that makes a total of 18 for our total sample size. Now, df1 stands for the degree of freedom in the numerator. Some computer programs refer to it as the degree of freedom of the factor degree of freedom. But basically, degree of freedom of the numerator is always just defined to be 1 less than the number of populations. Basically, it's how many rows you have minus 1. So we have 3 rows, so minus 1 would be 2. So df1 is just I minus 1, or 2. And then the degree of freedoms in the denominator, or the error degree of freedom, is always the total sample size minus 1, which is just capital N minus 1. So df2 is just going to be 17, 1 less than that. And as I said before, you add up the total sample, each of the individual samples, and that will give us capital N. And also, why do we care about this? It will allow us to interpret our p-value from what we sometimes call an F table, and we'll talk about that a little bit later. So the first thing I wanted to mention is, in order to calculate the F statistic, there's a lot of basically, it's never typically done by hand. It's almost always done via software, whether it be in R, in Excel, or in the TI-84. So what I want to show you next is how to calculate the I statistic. But basically, you just need to enter in your sample data into the calculator and go from there. And it's very similar to the chi-square statistic, where there we had to use the matrix menu to enter in our table of data and our expected counts in matrix A and B. Here we just have to enter our data in as lists, because you don't have to go through the whole expected count procedure in this particular case, because all of the Anova is based on all of the standard deviations and everything in a method that we're actually not even going to get into. But basically, if we can use list 1, 2, and 3 to enter in our 3 individual lists. So if we go into stats, we can edit our lists. And basically, we'll just type them in here. So let's start with winter as L1. So 264.2, 187.7, 291.1. I'll continue typing these in and continue after I'm finished. Now that we have all the data in, we can calculate the Anova value. So basically make sure you have everything in L1, L2, and L3. And again, you could expand up to list 6 if you had more and more populations that you're analyzing. Now I'll quit back to the main menu. And if I go into stat tests, again, where a lot of our stuff is, we can find Anova somewhere in here. So scroll down a ways, it looks like it's at the very end. H option is Anova. And then basically for Anova, you just then need to enter in your list separated by comma. So I could go second L1, comma, second L2, comma, second L3. And this should get what we want in calculating our F statistic from here. And again, I want to talk about more about what that means and so forth. And there is a warning here about the standard deviation. I'll talk about why that's relevant in a later video. But let's go ahead and calculate our F statistic. Again, in a lot of cases, this is something where you would be given the value on, say, an exam or homework, or asked to do it in Excel or R, or even using a calculator. So here our F statistic is equal to 27.52 approximately, if we're rounding that off to the nearest hundredth. And again, if you've ever experienced these sorts of statistics before, which again I probably imagine is not the case for any of you, it's very much like a chi-square statistic where the larger it is, the smaller the p-value, and again it tells us information about the resulting distribution. And right off the bat, seeing this as a very high number means that it's very strong. The bigger it is, the stronger it is, and it also means there's a smaller p-value. And when we're using statistical software, we often also get a p-value, which has the same exact context as p-values and other things. The smaller it is, the stronger the evidence is. And notice that this one, again, is times 10 to the minus 6th power. Very, very small, so 5 zeros, and then 9, 5, 6 for our approximated p-value here. Which, is super strong, would be less than any typical alpha value. So that would be less than, again, we're not given an alpha in this particular case, but that would be less than any normal level of significance. So we would say this would be very significant. And our conclusion would be to reject the null hypothesis when we get such a small p-value. Meaning that those means are not the same. There's very, very, very low chance that our null hypothesis is true. So we decide in favor of the alternative hypothesis, and our conclusion should be that there is a difference between the mean values of the different populations. Again, we don't have any conclusions about which is higher, which is lower. If we just look at the data, we might conclude that spring is the largest, the control is the smallest, and winter is somewhere in the middle. We could look at box plots for the data, kind of compare those things. Again, we don't want to look into any of those analyses further, but that would be the next step. So we could, now that we know there is difference between the data, we could then start testing individual, we could then run a 2-sample t-test between winter and spring, or spring and control, and kind of look into this further. But it gives us a starting point for our statistical analysis to see, okay, should we really be comparing some of these different groups going a little bit further? And actually talking a little bit more about the F distribution, much like with the chi-square distribution, it depends on the degree of freedom. How our book describes an F distribution is it always does it using df1 and df2, using the notation F parenthesis df1 and df2. So in our particular case, our distribution would be F parenthesis 2 comma 17, which just means the degree of freedom of the numerator is 2, aka 3 populations, and the degree of freedom of the denominator is 17. And it would look something a little bit like this particular density curve. You could look up there again. The shape is going to change a little bit based on different parameters, as you can see in a couple examples from the text. But just like with the chi-square distribution, the F statistic is going to give us a position on the curve from left to right. It will always be positive value, much like the chi-square test statistic must be positive. And when it's really, really big, it just is going to be really, really far away, which is going to result in very, very small portions of very, very small probability. And when you see values more like 3 or 4, it's going to be more, in the range of 1, 5, 10%, again, depending on those parameters. And even in our calculator output, you can see the degree of freedom of the factor, again, which would be called the numerator here, df is equal to 2, and then the error degree of freedom, which, I just realized there is a typo in the packet, and I forgot to correct this last semester, but it should be n minus I for degree of freedom of the denominator, which I noticed because notice the calculator is not in agreement with what I said earlier. So I apologize for my error from before, but the degree of freedom of the denominator is actually n minus I, not n minus 1. An easy mistake to make because the degree of freedom of the numerator is just I minus 1. And actually, this is a mistake that was in the book. I think they've corrected it, but in my packet, I have forgotten to correct it. But yeah, it should actually be 15 as the calculator says, because it should be n minus I. So apologies for that mistake there. But obviously you could check it with your with a calculator software, and it will tell you those things. But again, let me go ahead and correct what our particular F distribution, and every F distribution will have a different shape based on each of those degree of freedoms. And I believe we can even graph it with our calculator. If we run the Anova, actually, it only gave us that output. So in a lot of those other types of statistics, it actually allowed us to graph those outputting distributions in the calculator window, but it appears as though it won't do this here. I'm sure you could do it using R or Excel or certain other statistical platforms. Some of them could come up with a graph, but this gives us the sense of the general shape, which again, they are non-symmetric, kind of similar to your chi-square distribution. Again, the point of an F distribution is just, it's another different distribution, and in stats, there are lots and lots of different distributions for different situations. But the F distribution is just for dealing with analysis of variance, the specific procedure which is designed to look at lots of different simple random samples from different populations to see, is there a statistically significant difference between the data sets. And in the next video, we'll look at another example, but just the last thing I wanted to mention is that we're assuming the original populations have the same standard deviation, of which we do not know. Now, the thing about that is, like in this example where we're measuring plant biomass in different cases, why would each of these groups have the same standard deviation? Does that even make sense to begin with? But basically, that's an assumption we're making mathematically for Anova to be correct mathematically. But there is an allowance for a little bit of variation in the standard deviations, and it will still be approximately correct. So the rule of thumb says the results of the Anova F test are approximately correct when the largest sample standard deviation is no more than twice as large as the smallest sample standard deviation. So basically, what this is saying is if you're analyzing the standard deviations of each of those different data sets, those should be, none of them should be more than twice as large as another. Like say this one's 10, and this one's 15, and this one's 20. They should all be reasonably the same. But that's kind of where this warning came into play. It said the standard deviation for winter is almost 3 times that of the control group. And you can see like some of the data points in winter were a lot larger than the others, which, were not vastly different from control. So we can sort of see that this standard deviation is large compared. There's not a ton of variation from spring and control. So because the data is, the more variation, the worse off it is, just like always with any statistical test. But in this case, we should be a little bit careful with our results, but it being as significant as it is means that it's still probably okay. Or even that being said, maybe we could do a test directly with spring and control to see what level of difference those data sets have at the end of the day.